we go. I just had to turn it off and turn it back on again. And of course, right as I did that, the dog went crazy. You should have it now. All right, there we go. I heard it on my test. Yeah, that was a crazy thing of happenstance. I don't know what happened. I had to unplug the audio device and plug it back in. You know, the standard IT crowd, turn it off, turn it back on again. I think I had managed to get my camera that took 2 months to come through working, and so now I have a blackboard and a camera. And I think the audio that's supposed to be on the camera overtook the audio from my normal setting, and I probably had to reset it. But as soon as I turned it on, the dog saw something. So it's like the luck of things. All right, so some things to answer what Bill was saying, which I was trying to do as was getting started. This is the last section of material. I'll cover probably most of it today, which leaves us Thursday and Monday. I have a pile of questions I've been going through for people in email examples on, especially in chapter 6. I think I might do a review of questions people asked this Wednesday and this Monday over top of me recording the videos. The one thing I will say is be careful with the difference between a sample and a population standard deviation. They have a slightly different calculation. If you pull the wrong one off your calculator, that multiplies through a little bit odd. But I'm going back through and looking at all of these questions that are coming in from everyone. Let's see, so that's that. I have sent to email the slides. So the slides have been sent via email. So you should have gotten the slides probably about 15 minutes ago. I haven't got them up to Blackboard. Blackboard and I fight. It seems to be a Monday thing. In fact, lately right now, I've had technology bad Fridays and technology bad Mondays, and most of it I think is I have a lot of things running, and there's some caching I have to optimize. I'm fairly tech savvy, but one of the things I haven't done is I haven't optimized the system yet. I got it up and running to make things work, and there's some maintenance of files and optimization. I think one of the things that happens is I end up with huge temp files from all the video and sound stuff kind of cramming up places, and I'll occasionally have to do things to take care of that, hence the little unplug things and put them back in that we just had here. And one of the things I've been having is iConnect locks me out periodically, and it's usually like a cookie thing. And so when I was going to dump the slides up on Blackboard, my iConnect was timing out, and so I sent them out into email really quick so you would have a copy of them until I went back and just cleared out the cookies and cache on things. Because if I clear out the cookies and cache, I'd lose kind of all the streams I was in the middle of because they're also in cookies. So it's a 6 of one, half dozen of another. I'll rectify that shortly. Blackboard's a nightmare at all times, Cheryl. Blackboard is always a nightmare. And I am not a fan of using it as a resource. About the only thing I like using it for is announcements, and even then, I guess because I've always taught with other tools like Pearson or WebAssign, and what was the other one? There's Pearson, there's WebAssign. I think the other one became WebAssign when the two publishing companies, Wiley Plus, sorry. I never liked duplicating information, and so I've tended to use Blackboard or even Canvas when I used Canvas as just a repository of announcements. This whole situation is having me reapproach that. I'm trying to find a better way of centralizing things. I am of my generation. I'm an emailer, and I tend to send emails out with relevant information more than anything. I have been noticing that with more and more people using their phones and whatnot, email isn't a first go-to. So we'll find ways there. Dialogue is always good. Asking these questions. Pearson is not a bargain either. Yeah, I will say over its alternative, which is doing the homework on paper, handing in the paper, getting the paper back, it has its benefits. Like, well, in fact, those benefits outweigh its problems. It's the truism of life, right? Right. Something is going to be wrong with everything. It's which problems do you take on? And for the response you can get with the videos on Pearson, the ability to send my instructor things back. I think the thing that's different for me now is normally in course of a semester, I the as an instructor I only get like two or three. These are my problems during a week, and I email the person with them going through in a normal semester. Here, because everyone is focused in on the online, I'm actually getting a flood with them, and I'm going through. Cheryl, if you missed, I'm replying to everyone. Doing a Monday night video dump. One of the things to check when you're doing the confidence levels in any of the statistics is if it's using a sample statistic, use the sample standard deviation. There's a huge distinction between S and sigma, and it usually ends up being enough to significantly throw the answers off because the sample gets divided by n minus 1 square root versus the n square root in the standard deviation. That for a population. And from the two I've looked at, which weren't you two yet, but I'm noticing you're asking questions around the same problems. That was the case. So I'm going through, right now, I think I have two of Bill's to answer, one of Cheryl's, two of Bill's. I'm going through them in order. And then a couple from Jay, and I think one from Matthew. I'm trying, there's in through there, I have about 5 of them, and I've gotten through about 4 of them. So 4 previous coming through. But the pattern I'm seeing from the 4 previous that came through, that would be the thing I would tell you to look at first, is check what the standard deviation is. Yeah, it was a confidence interval 1, I think, or at least Bill's was a confidence interval 1 on chapter 6. All right, so we will probably talk about everything in chapter 9 they're going to talk about, which is the first 2 sections, section 9.1 and 9.2 today, and maybe a little bit on Wednesday. The rest of Wednesday and Monday, I'm going to be taking all these example problems people have been sending me and talk about them and answering questions in here if possible. Correlation and regression is probably, if I want to say everything you've done before sums up, this is probably one of the crowning points of everything we've been doing before. And it looks at the relationship between 2 variables. So I guess I'll get plugged into this. Continue to send me the emails. I am plowing through them. My email volume is about 20 times what it normally is, and so I'm about 40 times slower in my responses, and that does not make me happy, but I am working on them. We're going to talk about correlation, and there's an amazingly well quoted thing from interpreting statistics, and so I'll say this right off the bat: correlation does not prove causation. At the best, it suggests. If you have some model that thinks that one variable causes a result from another, correlation is the thing that can help you prove that. But just because there is a correlation does not mean that the 2 things are caused. And one of the things you'll find is people will learn correlation and they're like, I can take 2 variables and I can find the root cause of it all. And there are some great examples of 2 variables that seem to coincide in their change, but they're not correlated, or they're not causing each other. What was the one I saw? I think it was number of surfing shark attacks and the number of cars on the LA freeway. and whoa, the number of cars relate directly back to and is it the pollution causing the shark attack, right? Wait, if these things caused each other, right, the mechanism for it would have to be related. And what tends to happen is when you compare two things, things have cycles, and sometimes cycles fall into sync. There's a beautiful experiment you can do. You can take multiple pendulums and you can set them down, and they'll eventually all sync up, and then they'll fall out of sync again. It's just the small random fluctuations in pendulums. Eventually, they will all look like they're moving at the same time for a little bit, and then they'll fade away from that. Just because things line up does not mean that there's an underlying root cause. It could just be the fragment of time things are happening. It could also mean that there is a deeper correlation. And I'll use the freeway traffic versus shark attacks. Could just mean that more people are going to the beach, which floods up the freeways, which leads to the shark attacks. So the freeway isn't the causation, right? It's the change in personal habits that is causing both things to happen. And so we have to be careful with what we're going to learn here, correlation. It's a way of looking at two variables and to see if it is possible that they're related. We need to always get more information once we get something in statistics. And at the best, it will be helping us prove a mechanism that we think is underneath. And I'll show you some examples, but we're going to first start with the idea of what it means by two variables. And we haven't done two variable things, right? We might have plotted things in two dimensions in our graphs, but we're definitely going to do two variables. And so to do that, we're going to look at a relationship between two variables. And we're going to make them a pair, an XY pair. Now, from geometry, I hope this is showing properly. Yeah, it is. From geometry, XY pairs fall into a very specific way of measuring them. Descartes did this. He came up with the Cartesian system of putting things onto a grid so that you could talk about its location in two numbers, measuring in an X direction and a Y direction. And those two numbers can represent different things. In functions, we tend to say X is independent. You're allowed to change the value of X, and whatever you change the value of X, it gives an output in Y. When we look in statistics, that independence we'll call our explanatory variable, right? It explains the system, and the dependent variable is the response to that. And so what I want to do here is I want to switch over here for a second. Yeah, yellow will do. This is what we mean when we think of graphing in XY. Is that we have an axis X and an axis Y. And any motion in this direction changes the X value. And any motion in this direction, should put either way, changes the Y value. So we list every point in alphabetical order, X, Y, by a pair of numbers. So let's say I come over, we'll start at an origin or a starting place that is 0 on Y and 0, or 0 on X and 0 on Y. And I'll put these up here. It's called an ordered pair. And it describes a relationship between two numbers. And that relationship graphically comes out. Say I come over 2, so 1, 2 in X, and up 4, 1, 2, 3, 4. That point is 2, 4. There is no other pairing of 2, 4 that represents anywhere else in space. And so each point in space, I'll go down here and we'll say that's 1, 2, 3, that's 4, over 6. We'll say that's negative 6 in x and negative 7 in y. Came back 6 and down 7. And so each point in space, anywhere I map on a point in space, can be represented by 2 numbers. Well, relationships between points, right? Any 2 points make a line. If I were to draw my line properly, let me see if I can do this. And if these points were to relate something that had a relationship that was defined by the line could have an equation, a way of talking about how whatever was generating these points of data could predict other points of data. It could predict being there or there, because the line is the rule. And the line is the rule that determines any point that falls on it. And lines have a formula of y equals mx plus b, where m is the slope, x is our variable, our explanatory variable, and y is our response variable, and b is this point here where it crosses the y-axis, called the y-intercept. And so the fact that a law or a rule can calculate these 2 numbers for me is what mathematicians exploit. So let's go back to our statistics here and say that we can map data to an x and y value. And in doing such, we can look for rules that connect the data. In fact, specifically, it would be nice to know if our rules were on a line. And we say there would be a linear relationship between the data. Well, what we can do is we can make a thing called a scatter plot, where we take all the data we measured in the 2 different variables we found and plot them on a graph. And so the independent variable takes over the x, and it's measured on the horizontal axis, and the dependent variable is y measured on the vertical. And we can determine whether a linear correlation exists between the 2 variables. And so what we're saying here is we've taken these rules of geometry that says between any 2 points there's a straight line, and that straight line has a rule that will predict any point on that line. And that's a thing from geometry. And algebra turns that into a thing about numbers. And statistics says, well, if there is a rule that makes predictions about our data, and that rule is linear, so we're borrowing things from geometry so that we can map rules to numbers. And statistics is, I think, really where we fully abstract this. And so this is what we end up happening when we get correlations. Each dot is 2 values, the exploratory x variable and the response y variable. And we plot the pair of values on a graph. Now notice that kind of sort of follows a line. It's close to a line. And so this line is decreasing. So its slope, if it has y equals mx plus b to be its equation, its slope's going to be less than. And so we say that's a negative linear correlation because the slope of the line is going to have a negative value. And this data here kind of sort of matches the line. It clusters around a line, and its slope would be greater than 0. It would be positive. And so we would say this is a positive linear correlation. This stuff here, well, I could make a line here. I could make a line here. I could make a line here. There's tons of lines I could make there, but none of the dots really kind of center around any one of the lines. And so we say there's no correlation. This looks like a parabola. The dots cluster around a curve. And that curve is nonlinear. And so they're correlated to nonlinear data. We're not going to look at this other than to realize it can exist. And it gets slightly more complicated. Luckily, most statistics we work with, even when you have things like this, you can look at them as, well, there's a linear part here, and there's a linear part here. We can divide them down. A lot of mathematics is simplifying nonlinear things into linear analogs. But for us, we're going to focus on these top two things right now. Finding linear correlations amongst data points. And when does this stuff, this clustered grouping of stuff, approach these nice neat lines? And I hope you can appreciate that if this is a collection of data, this data is really close to being on that line. If I wanted to predict what a future value of x would be, I could say, well, it's going to be somewhere around here because it clusters around this line. If I move forward in x, well, I'm going to be near that line. Just like here, if I'm trying to make a prediction of some x value over here, I'd say, well, if whatever rule is making this data, my future values are going to be near the line. And that's the power of having these linear representations, is we get the prediction from it. We can observe our data and put them as scatter plots, and then we can look to see if there's a linear correlation between them, and we can try to make some predictive use of them. So we can construct a scatter plot. And so to construct a scatter plot, we need to make these values turn into a graph. All right, so things I'm going to look for are my lowest value in x and my highest value in x, which I think are there, and my lowest value in y and my highest value in y. I think that's good. So I can now make a graph. All right, I want to do this graph paper style. So let's see if all this stuff works. All right, there's that. And I'll come over here. Okay. So I'm going to make my axes. So I have all positive values here. So what I'm going to want to do is I'll make my y-axis here. And I'll make my x-axis here. And our oh, thank you. Yes, 232 is the lowest on 0.9. In fact, the lowest x and the lowest y's match. Oops, that switched over there. Can't see the blackboard. That's odd. I've got the blackboard coming out of here, but not out of there. Fuck. Yeah, I see the scatter plot slide only. It went all weird on me here. Do you have it now? I've got it. You got it now? There we go. Yeah. Technology! Alright. So, I'm going to need to get this back up for me. Alright. So my lowest value is 0.9, and I go up to 4.6 on x. So what I want to do here is I'm going to figure out how many tick marks I need here. 0.9 to 36. I think I should do them by 0.9s. And so, yeah, that works out nicely here. 4.6. Okay, so 4.6. So, make my graph. Let's try 0.3, 0.6, 0.9, 1.2, 1.5, 1.8, 2.1, 2.4, 2.7, 3.0, 3.3, 3.6, 3.9, 4.2, 4.5, 4.8. And so I can fit all my X data there. All right, counting by 0.3s. I hope that works. And then in going up, I need to go from to 1,157. So let's see here. So let's see. 1,200, I think I'll do. I'll go by hundreds. That's 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, 1,100, 1,200. So all our data will be within there. All right. So we get at least a half decent range of things. All right. So my camera finally came in yesterday. Still seeing if it's working fully. All right. So 0.9. So I'm going to make a dot for each piece of data. So my first piece of data, looking back at the list off the slide, is 1.8, 604.4. So if I look at my data, my first piece of data, my X value is 1.8, and my Y value is 604.4. So I'll come to 1.8 and up to 6.4. So I have a dot somewhere in there. I'll actually use a different color for that. We'll go below. Alright, so that's my first piece of data. My second piece of data is 1.3, 434.2. So I'm going to repeat this. I'm going to go to 1.3, just somewhere in here, and then 434, just somewhere about there. Really sneaky thing, right? I've got 2 points. It always looks like a line when you have 2 points. I remember when I first started plotting, it's like, oh, it's going to go, this is going to be the trend, and then you get the rest of the data and realize that was just your brain playing tricks on you, because that's what brains do. So we get 2.4544. So I come over to 2.4 and up to about 544. It's in there. Slightly higher than that other dot. 1.5 and 370. So 1.5 and 370 in there. 3.9 and 742. So 3.9 and 742. Right about there. 2.1 and 340. So 2.1, 340. 0.9 and 232 in there. 1.4 and 262.3. So 1.4, 262 out there. And 3.0 and 441. 3.0, 441. And 4.6 and 1157.7. So 4.6, 11757. And there we have our scatter plot. We have our data set up so that we kind of have our data spread out. There is kind of a linear thing going on here, and this is what we're going to look towards, is in general, this is increasing. Now, back in the day, they used to make rulers with a hole down the middle so that you could draw the line in the middle of the ruler. What you would try to do is you would find a place where you wanted to try to connect 2 points while having as many points above and below the line. So there I have 4 above and 4 below. And so if I connect these 2 points somewhere within there, now software doesn't now. And so for me, I want to say that's probably going to be our line of correlation. Something like that. And that's the general idea, is that we look for the general trend. And if we put half of the lines above and half of the half of the points above and half the points below, in general, these dots are sticking near this line. But some of these are really far away compared to others, so we'll find a way of improving this as we go. Sorry, I'm not sure if I'm in the camera or not, and I'm done. I don't want you guys to see me. I'm all like disheveled. All right, so we have what we need there. Let's move this through. Let's come back to our slides here. And so this is how we can make it what's called a scatter plot. We can work that scatter plot across. And again, what I sent you was a document on how to do that in Excel so that you don't have to plot all these things through, and we can estimate that line together. But a scatter plot is taking this chart of data and turning it into this relationship on our data set. And so where we have each dot representing a piece of data. And we can see there's a general trend. All right, I probably have this line a little bit shallower, but not by much. All right, so let's see what we can do with this. Let me get back to the slide here. All right, and there's what technology did. I'm not too bad. I didn't do too bad. I think my upper left-hand point didn't rise up as much, but I got the main features, right? I've got these two here and this coming across, and these two, and then those three off to the side. Yeah, let's peek back and forth here. Whoops, wrong one. Yeah, I didn't do too bad. I didn't do too bad. The far right side is not as good as it could be, but you know, by hand. And if I was doing this for a job, and I needed to do it by hand, I'd use graph paper, and I'd have these sections measured out a little bit better. But I wanted to quickly get it up on the board so that we had an idea of what this would look like and what the process would be to construct a scatter plot. It is a big stretch for me to say this is generally moving in a line, but it's not a horrible stretch, right? I could imagine that the CO2 emissions of some country in here, right? If the GDP was related, if there was a correlation between the amount of emissions or the amount of fuel they burned to make their capital, then some country in here should be logically between there and there, right? I would predict, hey, maybe the country's there. And that's the idea of the predictive power of this. Some country comes in here, and it's somewhere on here, it should be within this range, right? The general nature of this, the linear correlation of this data, is implying that I burn more fuel to make more money. It's a very, very complicated thing, but this generalization is probably going to do us well. And this correlation probably does talk about causation. Notice probably, likely. And so we want to figure out how we can measure these clusterings of dots, how we can talk about how these two variables are related to each other. And so this says it appears to be a positive linear correlation. Reading from left to right, as the gross domestic product increases, the carbon dioxide emissions tend to increase. I'm going to skip the student GPA one. I'll show it here. I won't redo it on the board. I think we have the idea of we map each point out, and graph paper is nice for it. And this gives this scatter plot. And it does appear that there is no linear correlation between the hours of exercise and your grade point average. And so there does not appear to be a correlation. Again, please notice the word choice. We're not saying anything with certainty. We haven't even measured these values yet. All right, I'm going to skip this for right now and want to talk about the correlation coefficient, because this is the ugliest equation I have ever seen. And I want to talk about this, because this is how we're going to measure how good these values are. Look at this. This is a mess. I know a teacher that makes everyone do this by hand, just like we did the standard deviations by hand. In fact, I actually know a teacher that teaches this that does not allow the students to use calculators, and they have to do R values by hand. And R values are probably, if there are two things that are used in statistics a lot, it's R values and P values. And we finished the P values when we were talking about rejection intervals and hypothesis testing. And so the thing you did with the P value was you'd figure out if you need it, if your hypothesis, if you rejected the null hypothesis or not. And it was a way of measuring against a claim. R values are ways of measuring against the idea of if something you're observing is correlated to something else. And for an example of correlation statistics, I was helping out a business major who's doing baseball management a couple years ago, and they were they had a hypothesis that a particular batting statistics drove the success of a team. And so we took that batting statistic and we tried to correlate it against every team to see if the success or failure of that pitching statistic was consistently a measure of this one team. It turned out it wasn't. Some teams actually did better in this pitching statistic than others. And so there was a combination of things going through it. Didn't help their hypothesis. But R is how we measure how well two variables correlate. So let me show you some R values before we dig into what the calculation means. I just want you to stare at that calculation and go, because it's ugly. I don't hear all the yeahs, but I'm making an yeah. All right, let me get over here. Is that working? All right, I'm going to drop over, and I made a program that does correlation coefficients. Let me make this a little bit bigger on the screen here. Let's see if you can see this. That's not what we want. Why are you not seeing this? Uh-oh. There that is. Coming. Let's go back. That's there. 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 Alright, let's see if I can get you guys to the right place. There we go. Alright, so what I want to do is I want to focus on the R value. I want to make this a little larger on the screen here. I'll move this over. Alright, so what I've done is I made a program that I give it an R value and it randomly creates some data points here. so that we can see how an R value affects the data and what comes out of the R value. So the first thing I'm going to do here is I'm going to just put an R value of 0. And so this thing that we measure, this correlation coefficient, which is what R is, when we measure it, if it gets a numerical value of 0, notice there is no overlying pattern in here. Human beings, being what we are, we find patterns like, hey, it looks like there's a line there. Well, it also looks like there's a line there. It also looks like there's a line there. We're bad at this, right? Human beings love to find patterns when there isn't one. We don't do random well. And so that's why it's good to have a way of measuring it. And so what that measurement does is it adds up the distance between each point. So the distance from this point to this point, and it does that for every point. And then it adds up the distance from this point to every point. And it tries to find if there is a set of lines that minimize the distance. And it turns into that ugly calculation. If there is one, R gets a value. If there isn't, R tends towards 0. So I'm going to increase this value slowly. So I started at 0. I'm going to move R up to 0.1. Not much of a change, right? They're a little tighter, but all right, let's jump up to 0.2. So we're getting a 10% improvement in R values each time. 0.2, well, they are coming closer together. And I've done this so they all fit in one window, and they're relatively proportioned to each other. And so notice that they're not filling the whole space as much as they used to. All right, let's go to 0.3. There's starting to be a block of dots here that makes a big line, right? From here to here, and it's generally going upwards a little bit, right? It's still kind of a chaotic mess, but there's definitely a tendency in the overall data than there was with it being 0. So 0.4, right? So 10% increasements to show the data is getting closer and closer. And so here's an R value of 0.4. An R value of 0.5. 0.6. Now we're starting to see a general trend, right? It's positive and up. 0.7. Increase my R value. 0.8. There's definitely a line moving in this direction. 0.9. I could say that's linear. And then 1. And 1 is a perfect line. Right? All of those dots lie on a line. And that's the range of R values. They go between 0 and 1. And they tell you how close the dots are. So if I had this data, and I would run it through the calculation for the R value, I would get an R value of 0.75. 0.75 tells me that this data is this close to being a perfect line. While if I have 0, it's all over the place. There is no correlation. Now notice I only put positive numbers in here. So I'm going to put 0.98 in. So there's 0.98, and this is a positive line. I can do the opposite. I can go down to -1. And notice R values of -1 are a downward sloping line. But the same thing happens. When you're near the absolute value of 1, you're a perfect line. When you're near 0, you're more chaotic and not correlated. And so this R value that we can calculate how these different dots are close to each other tells us how closely they are correlated. So a negative 0.65 looks like this. If this was my data, and I ran it through calculating the R value, I would get that it has a negative 0.65 correlation. That's telling me that this grouping of data tends to decrease. And the strength of how it is correlated is 0.65. If I were to have an R value of 0.88, if I had this data, the fact that it's a positive number, 0.88, I'd put all the data in, it would spit out an R number of 0.88, and I would be going, oh, okay, it's 0.88, so it's tending towards positive, so the line is moving upwards. There's a tendency for the data to move upwards, and it's correlated by a factor of 0.88. So our R value tells us two things. How close our data is to being clustered around a line. If it's a 1 or a negative 1, it's perfectly around a line. Let me show that again. Here's a 1. Right? Perfect line. And here's a negative 1. Perfect line. The sign tells me the direction the data is tending. If I have a negative sign, it's sloping down. If I have a positive line, it's sloping up. And so our R value does that. But I want to make very, very clear the R value is something we measure. I put together this program to show different R values so that you could get a feel for it. And I could create graphs when I needed to. Like if I had a test, I wanted a very specific R value, I could create it. In fact, remember Chevy Chev all the way from the back? The actual mathematics I needed to do to run this in reverse involved a thing Chevy Chev have worked on. And so whenever I think of Chevy Chev, I don't think of his approximation for non-normalized data. I think of R values and correlations in R values. So R values are what we're going to call the correlation coefficient. And it tells us how strongly our data is correlated. There is a formula for it. And you apply this to each point. You add up, multiplying the XY value for each one of your points, and then you subtract from that, adding up all the X values, adding up all the Y values, multiplying that together, and you multiply the answer by N. Right? N times this over this. And then you divide it by the square root of the difference of your X, your average X value, and your average X value squared. Horrible formula. Horrible formula. And we'll get our technology to work on it for us. Coming across. R values do pop out of our calculators. All right. What I want to do here is the range of the correlation coefficient is from -1 to 1. You cannot have numbers less than -1, and you cannot have numbers greater than 1. And when they are 1, they make perfect lines, with the sign being if it goes up or down. And so if R equals -1, there is a perfect negative correlation, and it looks like that. 0. Of using your technology for it, Bill? Is that what you meant? Yes, I will. I'll get there. Right now, I want to know what this measure is, and then I want to use it on data. And if R1 is a perfect positive correlation is R1. And so these are all the different R values. All right. So this is calculating the coefficient correlation. We're going to do it on the data that we have here, that we did on the plot. We're going to calculate how correlated this data was. I want to start with the TI-84. And we're going to want to come in, and we're going to be doing 2 variable stats for a change. So, sorry, I have to clear some lists out here. Give me 1 second. Clear list, second L1. That clear list, second L2. I know you got a slide. You're looking at 2 seconds. I'm almost there. All right. So, let's see if this works. I'm going to enter in a list all of my GDP values. Looking for my TI-30 while doing this. So I know I put it here. All right. I'm going to have to do this on 2 calculators. So I'm going to use this data here, and I'm going to do it on the TI-30 first, and then I'm going to do it on the TI-84. I'm going to move some things about, and we're going to see if this camera actually focuses on the keys. So you got the first test of a calculator example. So try to have this table here somewhere handy for when you try it. I'm going to come here. Yay. All right, let's see if this works. All right, so the light's too much. Let's turn off the light. And is that enough? Well, I can read the memory cleared on it. So that's actually visible. Yep. You see, so you want to go second, stat, and 2 vars. That's the first thing we do on the TI-30 is use the second, the stat, and then choose 2 vars. Then when you come into data, it asks you to enter your x1, and once you put in your x1 value, so in this case it was 1.8, enter. Come down, then it'll ask for your y1 value, which was 604.4. And you repeat that for every value in the chart. So do that right now, the TI-30 people. I want to get the TI-84 out. All right, so on the TI-84, see, it's the glares on the screen that make this unreadable. This camera can now focus on it, and I can actually get the numbers to read, but the glare on the screen's really hard, and I've got an extra light mounted to it, but it's like, gotta find something, see the reflectiveness? It's like, so you wanna come into stat and edit, and you're gonna pick 2 lists. I've cleared list 1 and list 2. In L1, you do all your X values. Now the thing that's really, really, really important is L1 you do all your X values. Yeah, it's glare. I had the focus working. Yeah, I'll figure it out. All right. You enter all your X values, 1.8 to 1.3. But for L2, you need to enter all your Y values. They need to match. So when you do this, I put 1.8, enter, it drops you down to the other one, 1.3, and then so on. Then you come over for L2, and you have to make sure 1.8 is 604.4, enter, 1.3 is 434.2. And you match all the values going down for L1 and L2. Where did it go? That is so weird. I had this visible on the table, but I'm really thinking it's glare. And I'll work on the glare. I might turn off the backlight on the TI-84s because that TI-30 was easier to read. I'll figure it out. We'll get there. All right. I just got it yesterday. I just got the camera yesterday. So I was still working on the best settings for it. I was supposed to have it a month ago, but the first one didn't ship. So you enter both of those values. You got to keep your X and Y separated. Let me go back here. And so you enter the X and Y separate on all of these. All right, so I'm gonna come through and enter all these down. And I'm gonna do it on two calculators now. 2.4, enter. 1.5, enter. I'm just going down my X values on this one. So I'm doing this on the TI-84, then I'm going to switch over to the 30. 0.9, 1.4, 3.0, and 4.6. So list 1 is done. Come back over, 604, 434.2, 544.0. 370.4, 742.3. Oh. So on the TI-30, when you hit the down arrow to move between variables, it's exactly the same as a 1var. Cheryl asked when you hit the first variable how you hit the second. And when we did 1var, we had to type in the variable and then down arrow and it would let us get the frequency. In this case, we type in the X value, hit the down arrow, and it's going to ask us for the Y value on the TI-30. The down arrow is your tool. Okay, 742, 340.5. And I just realized something else that I can do here. And so we're going to take our time here. Try to get both of these lists on your calculators. If you have a problem getting the lists on the calculators, we'll work on those specifically. But I actually did something the other day that I forgot to bring into play. All right, I have my two lists on my TI-84. TI-84. So I'm going to come back to the camera here and see if I can fix this. All right. What's really weird for me too is where is the glare? I think it's actually the light on the TI-84 because the TI-30 it was easier to see. Let me see here. And I'm all twisted, mirror twisted, because I'm looking at it on one screen. Notice I'm doing everything in reverse. Yeah, I'm not sure how to fix this glare right now. So I'm going to go to stat, and I'm going to choose 2var stat. So the stat key, and then I'm getting an option for 2var. I hit 2var. It's going to ask me what my X list is, which I did L1, what my Y list is, which is L2. I'm going to come down and I'm going to hit calculate and enter. And it gives me all the statistics on the 2var stats. But if I go to vars, oops. I hate these things for this. And XY. Over on the equation button. So I have my stats in, I did my calculation on my 2vars, and I have done my 2var. There's two ways I can get to it. The first way, if I go to vars, and I come down to statistics, which is number 5. So the vars key down to statistics, I have XY, a sum, and EQ, test, and points. If I go over to EQ, there's a thing for the R value, lowercase r. If I hit enter on it, where did it go? Enter, quit. Come back, var, vars. Ah! And you can't see anything on the picture because it's all blurry. Okay, did I get all of these in? Alright, so I'm going to come back here and go to linear regression, where it puts in the two lists, puts in my line value. Alright, I'm going to try to put this calculator on the screen because you're not seeing any of this. And I get my R value right out here, so hold on. I want to show you the other thing I have. Bear with me as I add my new tech in. Where did you go? Wow, we are delayed behind here. Sorry, there's a delay here. Let me switch this over. All right. Here is my TI 84. Not as good as a picture, but I'm going to hit Stat. And I'm going to choose Edit. So I'm going to hit Enter. And then for list 1, I have to enter my data in. My only problem is seeing this as I enter. I'm going to move, hope this doesn't move up. So you should be seeing a big, ugly version of the calculator here. All right, so as I come down, so my first number is 1.8, enter, 1.3, enter. 2.4, enter. 1.5, enter. So one of the weird things that's happening here is my notes are on a stand, which is on the other side of everything I have here, and I've been jumping back and forth, and I do not like any of this. I will get it all worked. This is what happens when you add a new piece of tech to everything. You have to get through. So I'm entering all the X values on the TI-84. I'm trying to find a TI-30 version of this. At some point, Texas Instruments are not the most helpful people in the world. All right, so I have done list 1. I have done all the values. So I'm going to come over here to list 2. And now I need to make sure that I match my Y value to my X value. So 604.4, enter, 434.2. Are you guys seeing this calculator come up? Is this visible? Like, just say something in the background would be nice. Like, are you seeing this? And it should be similar to what you see on the TI-84. As I am seeing the software is showing that you are getting a view of this. I'm just hoping you are getting a view of this, because I'm trying to make this visible. This is so much better than pointing at the camera. So 434.2, 544.0, enter, 370.4, enter, 3.9 has 742, 742.3. I have been finding the software is a little touchy, so I'm like really afraid it's going to crash on me right when we're done. Yeah. As far as I know, Cheryl, there's no TI-30 video on this. And most stat videos use the TI-84s because they were sold specifically as stat calculators. The stats features put into the TI-30s were kind of a quick and dirty set of stats. They were sold as scientific calculators. So they're kind of like a quick way to check stats. If I knew of any videos for it, I would have been referencing them. Well, the TI-84s have a fairly ample source documentation because they were made for these. 1157 parts of it. What parts of it aren't you seeing, Bill? Because I've got, let me see here. I've got the keypad in the lower half of the screen. It's the top of the screen you're missing, right? Let me see if I can fix that. Is that better? I think I can keep most of the keypad on. Oh, okay, it's bigger than the screen. Let me fix this. I see what's happening. There. We don't need the logo, we just need the screen. Yeah, there is. It's that equation I showed you, Cheryl. Yeah, it's the left half of the screen. That's all this thing takes. Let me do this here. There we go. All right. All right. So I have my two lists in. Let me get back to the calculator itself. And so I will come to the stat key and I'll go to 2 vars for 1. Enter. And it asks for my frequency list L1, L2. And I'll calculate. And this gives me the calculations of the average X value, the number of elements, my min max, and my min Y. And so it gives me a snapshot of my X values. And what we want to do though is in the stats, there's a linear regression. And when we calculate this, it should be spitting out the R value, but it hasn't been. And this appears to be a setting on the calculator, which I'm trying to find right now because I have it working on one. Let's come back over here. And that's what I'm trying to fix on this version of it. Because what happens when I go to hit R itself is there we go. Whew, fix that. All right, this wasn't working, so let me show you what to hit here. So you want to put both of these in and come down to 2 var stats. You'll calculate it on lists 1 and 2. And it prints out a summary of the data, but it doesn't print out your R value. If you come over to vars, the vars key, down to statistics, and over to EQ, you'll have an option for R, lowercase r. And I just broke it. Oh, I had it working up on the previous ones right here when I did it. And then I put it back in and it broke it. Oh, I know why. Sorry. Stat. Come down and I calculate linear regression. There we go. There's the linear regression. Now I come over to vars and statistics. Over to EQ and down to R. And that's my correlation value. So on the TI-30s, once you have the X and Y values in, if you go to stat var, let me just get 2 of these in. And you hit calculate, it has the R value at the very end. So on the TI-30, once you enter the list in, your X and Y values, if you click the stat var key, just like the one, let me see if you can see this. No, I still get it there. So on the stat var key, so when I hit the stat var key, up top I get all my variables. I can see them over there. I can scroll over my variables. So on the far right of the variables is the R value. See if I get to it. So you get A, B, and R. There's a lot of variables for the two vars up top. And you hit the right arrow key and you'll get your R value as your last thing. Now I unfortunately cannot see my calculator except on the screen. I can see that it's focusing, and right there's R. Now I didn't enter all the data in right now on the TI-30, but once you hit the stat var, it calculates them all and you choose R. To enter your data in, you do the X1, you do 1.8, right? Skip past the screen. Scroll down, and you get the option for your Y variable, and you put your Y in. Man, that glare! If I can just get rid of that glare, I can see it focused in when the glare's not there. And you just keep hitting your down arrow to enter each Y and X value in pairs. So once you have them all in, you hit stat var and scroll over to R. Okay, well, at least I got the virtual TI-84 working. That's a start. Eventually, I will get them through. Well, Cheryl, I didn't put the example in. Oh, that's right. You're about 5 clicks behind me. I am well aware of the glare there coming across. The main thing is the keys. You want to hit second stat, choose 2var. Data, use your down arrows to enter both lists. And that's actually the hardest part, is just lining up your X and Y values. Then for both calculators, lining up the values is the hardest part in all of this. And then when you hit the stat var key, it just has a big long list up at the top that your right arrow key will slide over, and it gets you to the R value. All right. So that's how we calculate these. That's how I'm going to calculate them, is rely on the calculator. Cheryl, I'm actually going to try to get this camera to record me entering in these R values on this calculator as soon as today is done coming across. And I'll see if I can post that. All right, so that's how we find these R values and these coefficients. Or you can do this. You can make a table. You can multiply X times Y. You can add up all the XY values. You can multiply X squared, add up all the X squared values. You can multiply Y squared, add up all the Y squared values. You now have a sum of your X's, the sum of your Y's, sum of your X times your Y's, sum of your X squares and your Y squareds. You can take those values and you can plug it into this equation. We're going to work with the calculators. I will make a video on this data set slowly with the virtual TI-84 and with the TI-30 on the camera, where I can mount the camera above the calculator. I'll do that first thing after this tonight, and then I'll do the questions to chapter 6. And that suggests a strong positive correlation. In fact, large R values suggest good correlation. All right, so that's really all I have on R values for today. I definitely will be continuing this on Wednesday. Please, as a secondary note, you are not stuck with your calculator. Right? Just because you're taking an exam on Pearson doesn't mean you have to use the calculator. You can also use Excel. I have instructions on how to find R values on Excel. You are completely free to use the technology what to do. The R value is the measure of how correlated the dots are. So when I showed those example of the dots, if they're really puffy and far apart, it's closer to 0. If they're really close together and form a line, it's closer to 1. And so the R value tells you how strongly correlated they are. The closer the value is to 1 or -1, the stronger they are correlated. The closer the value is to 0, the less correlated they are. And so it's how close those clusters are. Look at that PDF that I sent you. I actually have a plot of different R values on it. The slide in the textbooks do some different R values. But you'll get an idea that positive R values rise upwards, negative R values go downwards, and the closer the number is to 1, the closer the data is to each other. So numbers, think of it as a percentage, and the bigger the percent is, the better the data is correlated. So we could say this is like 87% correlated. Percentage is probably not the best word for it. It does kind of sort of map into a percentage, and it does work with ratios of things, but percentage wouldn't be the word I'd choose. It would be like a confidence. We're 87% confident. We're 0.87 confident that these are correlated. Yeah, I would use it as a confidence value. All right, that's what I have on R values, is what they are on technology. I'm going to make 2 separate videos here. One for the TI-30 with this data list. If I can find it again. And strong correlations have values closer to 1. Weak correlations have values further away from 1. Let me, both positive and negative. That's the data list. So I will make 2 videos with that data list, one on the TI-84, using that virtual TI-84, and one on the TI-30. I'm looking for how I can avoid that glare that always seems to come up. Might put the camera off angle to it. All right, I'm going to do that now, and then I'm going to start answering your questions through email and try to finish the rest of the questions. We will have another lecture on 9.1 and 9.2 on Wednesday, and then Monday, any questions you have, we'll deal with questions. Okay, talk to you soon.